So the first one that I'm going to give is the solution to practice set number 10, number 3C. Okay, so in number 3C, I also gave a correction on this problem. There was a typo, so I sent a couple of typos that were in this problem set. So in 3C, you had y was equal to k times e, k1 times e to the x plus k2 times e to the 2x. And then you had to verify that this was a solution of the differential equation, y double prime minus 3y prime, so this was the type over here, plus 2 times y equals 0. If you didn't catch this correction, then that might explain why you might have had trouble with this problem. So if we want to make sure that this is going to be a solution of this equation, we're going to take the first derivative, the second derivative, so that I can plug in the first derivative into the second term here, and the second derivative into the first term. And so I'll have, first, the first derivative is going to be just the derivative of this whole thing, which is k1 times e to the x, because k1 is just a constant, and the derivative of e to the x is just e to the x. And the derivative of e to the 2x is e to the 2x, but I need to multiply that by 2, which is the derivative of the inside. So that means the second term here is 2 times k2 e to the 2x. In the same way, if I want to find the second derivative, I'm just going to take the derivative of y prime. And so I'll have still k1 times e to the x plus, and then derivative of 2 times k2 times e to the 2x. Well, here, this is just a constant, so there's really no difficulty in using this term over here. So I know that the derivative of 2k2 e to the 2x is going to be 2 times k2 times the derivative of e to the 2x, which once I differentiate, I bring a second 2 down, and so this becomes 4 times k2 times e to the 2x. Now what I'm going to do is plug in y double prime into the first term of the equation here, y prime into the second term over here, and then y into the last term over here. Hopefully the arrows haven't gotten too confusing. So that means I have k1 times e to the x plus k2 e to the 2x. I'm sorry, what? Oh no, this is double prime, sorry. Double prime means I'm plugging in this one, plus 4k2 e to the 2x minus 3 times y prime, which is this expression over here. So that's k1 e to the x plus 2 k2 e to the 2x plus 2, and then I plug in just the original expression that I have for y. I'm just verifying if this type of function is a solution of this equation. That means here I have k1 e to the x plus k2 e to the 2x, and this is equal to, just create a new line over here. So now what I'm going to do is get rid of all the brackets and see if this ends up being equal to 0. I don't know if it's going to be equal to 0. I'm hoping that everything is going to cancel out such that it equals the right-hand side. So if I take out the first brackets, nothing changes because there's no constant in front. So k1 e to the x plus 4k2 exponential of 2x minus 3 times k1. So here I'm going to have to distribute to both the first and the second term. So minus 3 k1 e to the x minus 3 times 2, which is minus 6 k2 e to the 2x. And here, same thing, I'm going to have to distribute to both terms. So I'll have plus 2 k1 e to the x plus 2 k2 e to the 2x. All right, so here I'm going to combine all the terms that have an e to the x. So this is e to the x, e to the x, and e to the x. That's k1 minus 3k1 plus 2k1, which ends up being just 0. Right? So 0 times k1 times e to the x. So that becomes 0 over here. And then plus, I combine the terms that multiply e to the 2x. So I have 4 minus 6, which is minus 2 plus 2, and that's also equal to 0. So that means that this whole thing, everything cancels out, and it is actually equal to 0. All right, so what that tells me is that the function y is equal to k1 times e to the x plus k2 times e to the 2x is a solution of the differential equation that I'm given, which is this one over here. Do I have any questions about this? No questions, no questions. Okay. Oh, all right. Okay. Okay, so this was problem 3C. And maybe the problem here was really the typo. If not, then this is how you solve it. Then you had problem 4, in which you had to verify that something was a solution, and then verify what the particular solution of the differential equation was. So in 4B, which was the other one in which there was a typo, so I'm just covering those and hopefully we'll insist on the fact that there were typos in those problems, you have to verify that y, which is equal to c, some constant, times e to the 2x minus 2x minus 1 is a solution of the differential equation y prime minus 2y minus 4x equals 0. And you want to make sure that y of 1 is equal to 4. Okay, so this is our differential equation. So it's an equation that involves a derivative, and this is my initial condition. All right, so first thing that I'm going to do is verify that this is a solution, and then I'm going to just find the particular solution that satisfies this initial condition. Remember, this is a general solution because it still has a constant c over here, which we don't know the value for. We don't know what the value of c is going to be in this case. So first thing, find the derivative. Y prime over here is the derivative of this thing, which is going to be derivative of e to the 2x is just 2e to the 2x. So this is going to be 2c e to the 2x. And the derivative of 2x is 2. And then I'm going to plug in y prime into the first term, y into the second term, and 4x is going to remain like that because that's just the independent variable. So y prime minus 2y minus 4x is going to be equal to 2c e to the 2x minus 2 minus 2 times c e to the 2x minus 2x minus 1, and then minus 4x. I'm going to take out the brackets. 2c e to the 2x minus 2 minus 2c e to the 2x plus 4x minus 2 times minus 1 is plus 2, then minus 4x. And then I have that 2c e to the 2x cancels out with 2c e to the 2x. Minus 2 cancels out with plus 2. And plus 4 cancels out with minus 4. And so this is 0 plus 0 plus 0, which gives me 0. And this is a solution of my differential equation. Please raise your hand if you understand everything I've done. Good. So that means if I actually want to find the particular solution, now I just have to verify that this initial condition is satisfied. And so I'm going to force y of 1 to be equal to 4, which means that I'm going to make sure that when I plug in y, which is equal to 1, into the expression, in which case I get c times e to the 2 minus 2 minus 1. I get that this is equal to 4, right? So this is by plugging into the expression that I have for the function, this expression over here. So let me maybe just emphasize that a little bit. So what I'm doing for this first part is to plug into the function that I know y has to look like. And the next thing that I'm doing is just forcing this equation to be true because I know it to be true from this part. So by solving now, I have that c times e to the 2 minus 3 is equal to 4, which means that c e squared is equal to 7, which means that c is equal to 7 times e to the minus 2, right? Because this is the same as 7 over e squared. You can write it in both ways, and it's right in both ways. And so what that tells me is the general solution of this equation is of this form. If I want the particular solution, then I need the constant to be equal to 7e to the minus 2, which means that the particular solution is the function of this form whose constant is equal to this number. So the particular solution will be y, which is equal to c, 7e to the minus 2, times e to the 2x minus 2x minus 1. And because these two things are on the exponent of the same thing, so this is e to the minus 2 times e to the 2x, I'm just going to put both of these things on the same exponent. And this gives that this is 7 times e to the 2x minus 2 minus 2x minus 1. Right, so this is just another way of writing that first term. Can you please raise your hand if you understand this transition over here, the arrow that I just did? All right, I have, I think 4 hands that didn't come up, 3 hands that didn't come up. I just want to make sure that that's not out of misunderstandings, but just maybe laziness of pressing. Raise your hand. So if you have any questions, of course, you know, you can interrupt me and ask. Is this okay for everybody? Okay, so these questions were requested by Vicente and Sarah. Does this answer your questions? Did you find any mistakes or any things that you had kind of forgotten about? Oh, it was a typo. Yes. Okay, that makes sense. All right. Okay. So as long as you found your mistakes or you realize that there was a typo, so just make sure you go over my announcements. I know that sometimes there's a lot of them, but especially for typos, it's useful because otherwise you end up just questioning yourself instead of questioning me, which sometimes is really worth it. Okay. So I'll solve problem 5, I and H now. Let me start with. I'll start with problem 5I and then I'll do 5H. So in problem 5I, you have to solve the equation square root of 1 plus t squared times y prime minus t times y squared is equal to 0. And what I said for this type of problem, the first thing I said is if you have a y prime, write it as dy over dx if the variable is x or dt if the variable is t, because then it will become clear what you need to split, right? So where you need to put your equal sign, it will make it easier for you to evaluate this if you have written the derivative as d something over d something. So that means here I'm going to write this as square root of 1 plus t squared times dy over dt minus t times y squared, which is equal to 0. All right, now why dt? Well, because my other variable here is t, not x. So if this is what I need to do, I'm going to start by putting this term on the other side, because I know that I'm going to need eventually to multiply by dt. And so maybe I just need one term on the left-hand side, one term on the right-hand side. This is always going to depend on the type of equation that you have, but in this case, it looks like it might simplify my life quite a bit. So I'll have square root of 1 plus t squared dy over dt is equal to t times y squared. All right. And now I have, okay, so I have a term on the left-hand side, a term on the right-hand side, and we said the whole point of writing this as dy over dt is to be able to realize that every term that is in terms of y will have to go on one side, whereas every term that is written in terms of t is going to have to go on the other side. Right? Of course, just making sure that you are simplifying your equation in the appropriate way. So if this is the case, now what I'm going to do is divide both sides by y squared, because then I know that I will simplify this on the left-hand side. So I'm going to divide both sides by y squared. And I am going to also divide both sides by square root of 1 plus t squared. And that will cancel out 1 plus t squared on the left-hand side, and it will bring it to the right-hand side, which is exactly what I want, because then I'll have everything in terms of t on the right-hand side. And I'll have to multiply by dt so that I cancel the dt that's on the left-hand side, and it comes all the way to the right-hand side. That means if I do this on both sides, I'm going to get on the left-hand side just 1 over y squared times dy. And on the right-hand side, I'm going to have t over square root of 1 plus t squared dt. So now I have everything in terms of y on the left-hand side, everything in terms of t on the right-hand side, and I can take the integral of the left-hand side and the right-hand side. Can I see your show of hands for those of you who understand what I'm saying? Okay, I still have a couple of people that haven't raised their hand. Do I have any questions? All right. Okay, so please everyone lower your hands. So on the left-hand side, I'm going to integrate this right away. Remember, this is the same as y to the power of -2, right? And so when I integrate this, I'm going to get my, maybe just y to the power of -1 divided by -1. And what we said is when we're integrating this type of, when we're integrating to solve differential equations, we're only going to add the constant of integration to one of the sides, usually the right-hand side, because in the end, I would always end up combining the two constants that I find regardless, right? So if I were to put a constant of integration on the left-hand side and another constant of integration on the right-hand side, I would always end up combining those two constants of integration. So there's no point of unlabeling them different things when I'm going to combine them and put them just like under a single label, right? So I'm just going to put that constant on the right-hand side. However, in this case, we haven't integrated the right-hand side yet. To do that, I'm going to do the following. I can't integrate just t. I can't integrate just square root of 1 plus t squared. And that's particularly because the inside of this function is not a linear function, right? I have over here something that is a function of t. And so if I want to integrate this, I'm going to have to do a substitution. Now, the substitution is not too difficult, but I do have to do it carefully. So what I'll do here is I'll write u is equal to 1 plus t squared, and du is equal to 2t dt, which means that if I want to replace just t dt, which is what I have here, I'm going to have to multiply by 1/2, which is the same as dividing by 2. So now I can actually do the substitution. I have integral of t dt becomes du over 2, which is going to be du. I'm going to put a 1/2 over here. And then this is square root of u at the denominator, which is the same as u to the -1/2. Can I see a show of hands for those of you who understand this? Okay, that's good. Now, what I've done here is to rewrite the left-hand side as -1 over y, because y to the -1 means just y to the 1 at the denominator. And because I have a -1 at the denominator, I can just put that in front of the fraction. All right, and then the right-hand side can now be integrated because this is just 1/2 u to the -1/2, which if I integrate is going to be just u to the 1/2, and then plus a constant c, right? So this is where you put your constant integration. So now you'll have -1 over y is equal to u to the 1/2, but of course u to the 1/2 is not just, what am I saying? This is not just u, this was just a label for 1 plus t squared, which means that this is 1 plus t squared to the 1/2, just square root of 1 plus t squared, the whole thing plus a constant c. And now, because what I'm trying to solve for is y, I'm trying to get at the end y is equal to something, then I'm going to multiply both sides by y and then divide both sides by this. So if I first multiply by y, I'm going to have that -1 is equal to y times square root of 1 plus t squared plus c, which means that to find y, I'm just going to divide both sides by square root of 1 plus t squared plus c, and y is going to be equal to -1 divided by, maybe I'm going to put the c plus square root of 1 plus e squared. This is my final answer. Yeah, because I don't have an initial condition. Is this okay? Can I see a show of hands for those of you who understand this? All right. Okay, so this is number 5i. I think there's a couple ideas here that are worth thinking about a little bit. The first thing is that in order to get everything that's in terms of y on one side and everything that's in terms of y on the other side, I sometimes need to add or subtract before I start multiplying or dividing, right? So over here, a big part of being able to solve for this was to be able to put the term t times y squared on the other side and then divide and multiply by the terms I was missing. That's the first thing. The second thing is that sometimes we do have to use the techniques of integration that we talked about so much at the beginning of the semester, right? So we had a bunch of sections on how to evaluate integrals using, integration by parts, substitution, partial fractions, and a bunch of other things. And that means that if you're actually trying to solve a problem, you should be using those techniques, right? I'm not just teaching you techniques for you to say that you once learned them, but specifically within the context of the class, chances are that I'm going to ask you to use those techniques in order to solve a problem that's a little bit more complex or that integrates different parts of what you've learned in Calculus 1 and Calculus 2. Okay, so then substitution was a technique that we used over here, but the same could be true of using integration by parts, partial fractions, integrals of trigonometric functions, and so on and so forth. So it's important that you know how to use those. Do I have any questions about this problem? Can I see a show of hands of those of you who understand everything that I've said since the beginning of the class? Okay, less convincing these numbers. There's about 9 hands that went up. All right, so let's see if the next example maybe clarifies a couple of the things. Sarah, your hand is still up. Is that because you have a question? Okay, no more. So the next one is going to be 5h. And 5h is y prime is equal to x e to the x divided by 2 times y. So first thing is to write y prime as dy over dx. So you're going to write this is dy over dx, which is equal to x e to the x over 2 times y. And now, again, as usual, and you're going to see it's always the same exact type of problem. You have to bring everything with the same letter to the same side. So everything that's in terms of x to one side and everything that's in terms of y to the other side. Right? And so I'm going to multiply both sides by 2y and by dx. So multiply everything by 2y and multiply everything by dx. On the left-hand side, I end up with 2y dy. And on the right-hand side, I end up with x e to the x dx. And I'm going to have to integrate both of these independently, right? So the whole idea, again, I repeat it, but I mean, if you remember this, you remember basically everything that you have to do, as long as you remember the techniques, which is that you're always trying to get the same variable on the same side so that you can integrate each side independently. So integral of 2y, that should be a reflex. At this point, this is second nature. If it's not, it's a big, big problem. Integral of this is just y squared. And then the integral of x times e to the x, I'm going to have to evaluate using something else. So integral of x e to the x is definitely not just x times e to the x. So I can't just take the derivative of the second term. It is also not x squared over 2 times e to the x. So I can't take the integral of the first term and not the second, and I cannot take the integral of the first and then multiply it by the integral of the second, right? So make sure that you didn't write something like this, and if you did, that you cross it in big, with a thick red marker to say, no, this, you shouldn't do this anymore. Instead, we're going to try to solve the problem by looking at this over here and trying to see what else we can do. According to you, what technique should we use in order to evaluate this integral over here? You can say it on the mic or you can write it on the chat.
Integral by part.
Integration by parts. So we're going to do an integration by parts on that second one over here, which is going to use v is equal to something and du is equal to something. Now, the function e to the x dx, whether I differentiate it or integrate it, is going to be easy to evaluate, right? If I integrate it, it's just e to the x. If I differentiate it, it's just e to the x. But the function x over here, if I differentiate it, it becomes a constant, which is nice. If I integrate it, it's going to become another polynomial that's also easy to look at, but it's a higher degree, and so it might complicate the integral that I'm evaluating, right? So instead, I'm just going to choose this dv, so that when I differentiate it, I get something that's even nicer, right? So this is just 1 times dx, and it simplifies my life quite a bit. That means that du is everything that's left in this product. So this is x was the first term, so everything else has to be du. So this is x e to the x dx, which means that u is the antiderivative of this, which is just e to the x. And so I now know that to anti-differentiate, to integrate this, I'm going to have to evaluate v times u and then subtract the integral of u times dv. So this is going to be x e to the x minus the integral of u, which is e to the x, dv, which is dx. Now, the left-hand side still hasn't changed over here, and I'm going to get x e to the x minus integral of e to the x is just e to the x, and then plus my constant of integration, which I have to add on the right-hand side. All right, and from here, if I want to solve for y, I'm going to get that y is equal to plus or minus square root of x e to the x minus e to the x plus c. This is my final answer. Now, my final answer has to have a constant of integration or a constant over here for which I don't know the value, because this is just giving me the general solution, right? If I wanted the particular solution, I would need an initial condition, and then I would have to verify that that condition is satisfied, and that would fix the value for my constant. Show of hands for those of you who still don't feel so sure about what to do for this type of problem. People are more shy with this one. Okay, do you have any questions about this? All right. Lucky for you, even if you haven't had some practice, even if you haven't looked too thoroughly at practice set number 10, you have now a web work that's available that is due on Saturday. Yes, I agree, Juliette. Some look hard, but they are simple. That's exactly the case. The equations look extremely complicated, but once you start manipulating some of the terms, it ends up being a super easy integral to evaluate. There's really no big challenge aside from the example that we covered last time. That was a big challenge. We all agree on that. So you have a web work, and the web work, you have 15 problems with respect to differential equations. And I think because you guys are not used to working from home and just having to do homework, and I'm not used to not being able to help you during class, I'm going to try to do more frequent web works. Not in the hopes of giving you more work, but just in the hopes of being able to check that you're doing some of the homework and for you to realize what you are and what you are not understanding from the material of the class. Okay, so the web work is available already, and it is due on Saturday, I think, at midnight. Okay, so the idea of that is for me to be able to check which problems you were struggling with, because we're going to be figuring out the evaluation scheme for the class in the next couple of days. Do I have any questions about this? About anything at all? Now's the time to ask your questions either about the problem set number 10 or about the class in general. No. All right. Of course, yeah, I mean, you can interrupt me if there's something you have any questions. Oops. So in what we're going to finish doing today, so we're going to start a new section, which is called L'Hôpital's rule. I'm just going to explain the main idea. I'm going to do some very easy examples, and on Thursday we're actually going to get to the core of the problems that might be a little bit more difficult. I'm not going to give homework on L'Hôpital's rule from today to Thursday. I want you to focus on starting the web work. Okay, in the web work, be careful about how the problems are phrased, and make sure that you write down all of the information, that you're really careful with signs and everything. You know that web work can be tricky once you're trying to enter the solution. So for the next section, we have section number 2 in chapter 3, which is going to be called Indeterminate Forms and L'Hôpital's rule. And L'Hôpital. My keyboard keeps changing from English to Spanish, and so L'Hôpital's rule. Now, this is not the hospital rule, it's L'Hôpital's rule because L'Hôpital was the name of the dude that came up with the rule. Okay? That's write it in French. Now, I want you to, so I know that the chapter that we're looking at right now is called Applications of Integrals. This is not really an application of integration, but it was initially in this section because this chapter was supposed to have a third section, and in that third section we were using this this material over here. Now that third section has been cut from the material for the class because of course we lost some time. Online classes are more difficult, blah, blah, blah. We still are going to use L'Hôpital's rule later in the class, so we still are covering that, but you know, you'll forgive the placement of this in a chapter that's called Applications of Integrals when it is not actually an application of the integrals. And before I start with this, I'm going to ask you to remember to write down the limit definition of the derivative. So the limit definition of the derivative. And so limit definition of the derivative, you have 2 minutes to either look it up, but hopefully to try to remember it yourself. All right, do I have anybody that remembers the limit definition of the derivative and that would like to say it out loud or write it in length on the chat?
I think I have it.
All right.
It is the limit of h towards 0, where f of x plus h minus f of x over h.
Minus f of x over h. That's right, except for one little thing, which is that here the derivative is being evaluated at a, which means that we're going to need the x to be replaced by a, but that's the only thing. Right, so that's one possibility, a plus h minus f of a, the whole thing divided by h. Can I see those of you who remembered this definition for the derivative? All right. Now, I wrote f prime of a is equal to this, or f prime of a is equal to this. Does anybody know what the second definition of the derivative is? They're equivalent, but they can be written in a different way. Can anybody tell me what the second definition for the derivative is? Can I see a show of hands for those of you who know what other definition I am asking about? So some of you, who knows only this definition? Who has only ever seen this definition? I have to say I agree with your teachers from last semester because this is the one that's actually useful in order to evaluate things in Calculus 1. The other definition that you might have seen and forgotten it, but you probably saw it, is that f prime of a is equal to the limit when x goes to a of f of x minus f of a divided by x minus a. With this now on the board, who remembers having seen this definition at some point in life? Still no, eh? Who remembers having been to Calculus 1? Okay, good. All right, so these two things are equivalent. It's just that, it depends on how you defined a, like A and H and everything. So in the first one, what we have is essentially, let me see, we have like a function, maybe that looks like this. In the second one, we have a function that looks like this. In both of them, we have the point A over here with f of a. We have a over here with f of a. So in one of them, in the first case, we say that we're looking at the derivative that was the limit as we dragged a certain point over here. And in the first case, we just said that the distance over here was h, so that this point was a plus h, right? And so what we were looking at was the difference in the function divided by the difference in the difference in y divided by the difference in x, because we were trying to estimate the slope, and then this was the tangent line, right? So that means we had something like this. In the second case, it's the same exact thing. We're trying to evaluate the slope of the tangent line by looking at a point that's maybe at the same distance. But what we said is instead of taking h over here, the distance to 0, which is what we do here, what we're saying is let's take a point and let's take this point to A, right? And so then we're still looking at the difference between the values of y divided by the difference between the values of A, of x, and we end up with this expression for the derivative. Can I see a show of hands for those of you who understand and remember more or less how the derivative over here was found? Okay, good. So that means these two things are the same, but unluckily for you, today, eventually, we're going to end up using this one. Okay. Just remember that this is something that you learned at some point in life. It's not going to be too much, but as long as you remember that that exists and it's equivalent to the first definition, then you should be okay. I have Shine and Sarah with your hands up. Is there a question? All right, so now with this in hand, eventually I'm going to refer to it and then I'm going to come back to this page. But what we're actually looking at is a specific situation that we're then going to use this expression in order to solve. So what I'm going to ask you to do is to consider the following limits. Now, you thought you had gotten away from limits. You thought, I finished Calculus 1 and then I'm done with this. I'm never looking at limits ever again. And here they are to haunt you again. There's no way of getting away from this. We are going to have to do limits in this case. But you're pretty good at doing limits, presumably. So we're going to look at the following three. We have the limit when x goes to 1 of 2x minus 2 divided by x minus 1. The limit when x goes to 1 of x minus 1 squared divided by x minus 1. And the limit when x goes to 1 of 4x minus 4 divided by x minus 1 cubed. Now, you'll agree with me that first, each one of these limits is evaluated at 1, and each one of these limits has a factor of x minus 1 in some way or another. Aside from these things, I want you to look at the limits and to tell me what else do these limits have in common. What do these limits have in common?
They can all be factored.
They can all be factored. But if you were to try to evaluate this limit, what is the first thing you would do? Whenever we try to evaluate the limit, what is the first thing that we do?
Simplify.
Simplify. Before that, why do we need to simplify? What is the first thing that we need to do? Because if we can't avoid the simplifying, then we should avoid the simplifying. What should I verify before I try to simplify? Yes, you have to plug in the x, right? So the first thing that we would do is we would plug in x is equal to 1. Now, if I plug in 1 into this expression, I'm going to get 2 times 1 minus 2, which is 0. And then I'm going to have, this is divided by 0. If I plug in 1 into this expression, I get 0 divided by 0. And if I plug in 1 into this expression, I get again 0 divided by 0. Now, this was a problem, and you learned that this was a problem in Calculus 1, because 0 over 0 is not always easy to determine what this is going to be equal to. To remember why we can't always know this, we're going to evaluate these 3 limits because we know how to evaluate them, right? So the first thing I need to do is to plug in x, and if that doesn't give me a conclusion, then I can do something else. Okay, so in this case, I'm going to be able to factor them. So the first one is going to give me limit when x goes to 1 of 2 times x minus 1 divided by x minus 1. The second one is going to give me the limit as x goes to 1. And this is x minus 1 squared. So this is x minus 1 times x minus 1 divided by x minus 1. And in the third one over here, I'm going to have limit as x goes to 1 of 4 times x minus 1 divided by x minus 1 times x minus 1 squared. Right, so lucky for me, in all of these cases, I was able to factor things out in such a way that here I'm able to simplify, and this gives me the limit of 2, which is just equal to 2. Here, I'm able to simplify, and this gives me a limit that is equal to the limit of x minus 1, which just gives me 0. And this is the same as the limit when x goes to 1 of 4 over x minus 1 squared. This is equal to what? What is the limit of 4 over x minus 1 squared when x goes to 1? It's infinite, right? And the denominator is always positive, which means that this is always plus infinity. Otherwise, we have to, remember, you have to verify whether it's plus infinity, minus infinity. In this case, the denominator is always positive. So we're dividing by something really, really, really tiny that is positive. So we get something really, really large that is positive as well. So this is the whole point, the whole reason that we can't conclude from 0 over 0 is that here we had 0 over 0 is equal to 2. Then we had 0 over 0 is equal to 0. And then we have 0 over 0 is equal to plus infinity. That means from the indeterminate form, 0 over 0, we can't conclude what the result is going to be, right? Yes, Jesse, there's a question?
Yeah. So
Yep.
if we plug in the 1, like over here, it's 4 over 0.
Mhm.
So why is it infinity and not like no solution?
Because we're looking at the limit, remember? So when we're looking at the limit, we're trying to say, what does the function go to when x is approaching 1? So when we're plugging in x is equal to 1, we're assuming that x is equal to 1, not close to 1. And in this case, I don't want x to be equal to 1. I want x to be really, 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 really close to 1, but not exactly equal to 1. And so the denominator is going to be almost exactly equal to 0, but not exactly 0. And so the result is going to be a very large number, so infinite. But because the denominator is not equal to 0, the limit does exist.
Okay, thank you.
Okay, so the idea here is to say the indeterminate form, 0 over 0, doesn't allow me to determine what the result of a limit is going to be. So 0 over 0 might result in several possible answers. It could result in 0, it could result in some other number or some other constant, or it could result in plus or minus infinity, and I have no way of predicting it without doing some extra work. Show of hands for those of you who understand this. All right, so I'm going to just summarize that in a couple of remarks over here. So the first thing is that there is no way of knowing whether the form 0 over 0 means that the result, that the limit, will be equal to 0 to some constant or to plus or minus infinity. Right? So I have no way of determining that without doing some extra work. Okay, so there's no way of knowing whether this is the case without doing some extra work. The second thing that I want to notice over here is that the result is going to depend. So I'm going to write it down and then we're going to talk about it a bit more. So the result depends on whether, on how fast the numerator and the denominator are approaching 0. Okay, so once you're done writing this, please raise your virtual hand. Okay, so to talk about why this can be equal to different results, I want to start by understanding what it means for the limit to be equal to a constant, to 0, or to plus infinity. And to do that, what we're going to say is, consider, for example, this case. Okay, so we have the limit of 2x minus 2 over x minus 1 as x goes to 1. And what we said is it looks like as x approaches 1, you see the numerator over here is exactly twice as much as the denominator, right? Which means the numerator is going to 0. There's no denying that. Numerator is going to 0. The denominator is going to 0. But the numerator is twice the denominator, right? So it's 2 times the denominator, which means that if I look at the ratio, even though they're both going to 0, the numerator over here is still double what the denominator is, right? And so if I look at the ratio of these two terms, I'm going to have that as x goes to 1, the ratio is still going to remain equal to 2, right? And so if I look at the limit as x goes to 1, then I'm going to have that the limit is going to be equal to 2. So this is why I get something like that. And the reason is that, well, this is double what the denominator was. Now, if I look at the second case over here, same thing. I have that the numerator is going to 0, the denominator is going to 0. But then I can look at what the numerator and the denominator are actually doing. So the numerator is x minus 1, but it's x minus 1 2 times, which means that x minus 1 is approaching 0, and then it's being multiplied by something that is also approaching 0. Right? So it has 2 factors, both of which are approaching 0. The denominator instead has only 1 factor which is approaching 0, right? It only has one x minus 1, which means that the numerator is approaching 0 at a higher rate, so faster than the denominator is approaching 0, right? So this is like 2 things that are approaching 0 being multiplied by one another, which means that it's getting closer to 0 and faster. Whereas in the denominator, you have something that is, sure, going to 0, but there's only 1 factor of those. So it's going to 0, but maybe a little bit more slowly. Does that make sense for everybody? Yeah, so I have at the numerator something that's going to 0, but because there's 2 factors that are going to 0, it's going to 0 faster. So it's getting to 0 really, really fast. Now what that means is the numerator is going to 0 faster than the denominator. And so the 0 at the denominator isn't enough to counter the fact, to compensate for the fact that the numerator is going to 0 really fast, and the numerator ends up dominating. So the 0 at the numerator ends up dominating and ends up giving me something that is equal to 0. Jesse, is that a question? Yep, hands down. Daniel, do you have a question? I'm guessing that hand is coming down pretty soon too. Okay. Okay, so then we have the numerator here is going to 0 faster than the denominator, which is why the result ends up being 0. For the last example, again, we have a numerator that's going to 0, a denominator that's going to 0, but in the numerator, I only have 1 factor that is going to 0, or 1 thing that's going to 0, which means that I'm going to 0, but at a rate that's more or less low. At the denominator, I have 3 factors that are going to 0, which means that not only is one of the factors going to 0, but I have 2 other things that are also multiplying and going to 0. So they're also making this expression go to 0 even faster. What does that mean? Well, it means that the denominator is going to 0 faster than the numerator is. And so that means that the denominator in this case dominates. That 0 stays there, whereas at the numerator, it's no longer there. Right? So if I look over here, I can see that at the denominator, this is a term that remains, and that's why I end up with some constant divided by 0, which ends up giving me plus infinity. Okay, so what this is telling me is that if I want to look at what the result is going to be, what I need to determine is how fast is the numerator going to 0, and how fast is the denominator going to 0. Okay. And then if I look at how fast each is going to 0, I will be able to determine the result that I'll end up with. Okay, so this is the big part. How fast the denominator and the numerator are approaching 0. Okay. Now, we have been doing calculus for about what, 6 months now. And we know that when we say how fast, at what rate, what we're referring to is a derivative. So what this is suggesting is that maybe if I look at what the derivative is at this point, 1, 1, and 1, maybe the derivative will tell me what the result of the limit is going to be without having to do this work. Because in this case, of course, I was able to factor the x minus 1 in each one of these cases, and that made it easy to evaluate each one of these limits. But it's not always going to be that easy, right? It's not necessarily the case that you're going to have a ratio of two polynomial functions that you are, on top of it all, going to be able to factor in order to cancel the appropriate terms. If you had an exponential function, if you had a trigonometric function, if you had a logarithm or something like that, it would be a lot more difficult to try to factor those terms, right? And so we have to come up with something else. So let's see. What we're going to do, and today I'm going to go with theory. Theory can be heavy, so just stop me if you need. So suppose that we're trying to evaluate the limit when x goes to a of f of x divided by g of x. Okay, some function f divided by some function g. And we're going to see if I can recover the derivative, or if the derivative can tell me anything based on this. Okay. And suppose that this gives me 0 divided by 0. Okay. Of course, this is not equal to, because this is not a number, but it's like equal to. If I try to plug in, then I get 0 over 0, which essentially tells me that f of x is going to 0 and g of x is going to 0. In here, we're going to assume, so just for the sake of the argument, but this is not necessarily always the case. So we're going to assume that what's actually happening is that f and g are continuous, and that f of a is equal to 0, and g of a is equal to 0. This is not always the case. This is only telling me that f is going to 0 and g is going to 0. Okay. But I'm not going to focus on these technicalities. I'm just going to assume that this is the case just for the sake of the argument. Okay, so we're going to assume this. And now what we're going to say is, okay, well, what this means is that I have f of x over g of x is equal to 0 over 0, and that means I can't conclude right away. But what we said is, what if I look at how fast f and g are approaching 0. What if I look at how fast f and g are approaching 0? How fast means derivative. Right, so this is our classic. How fast? The rate means derivative. We're going to see how fast f and g are approaching 0. Well, lucky for me, I know what the definition of the derivative is. Remember, a couple days ago, we said f prime of a is equal to limit when x goes to a of f of x minus f of a divided by x minus a. I'm going to copy that again over here. So I know that just over here, derivative, and the derivative is given by the limit as x goes to a of f of x minus f of a divided by x minus a. Okay, so if I could somehow recover this formula, maybe I could come up with some interesting expression for the limit in terms of the derivative. All right, so here we go. Remember, we're trying to find the limit when x goes to a of f of x over g of x. Right? But the limit of f of x over g of x is the same as the limit of f of x minus 0 over g of x minus 0. So all right, now that seems like the most useless thing I've written today. Why do I care about this being f of x minus 0? Well, I know that 0 is equal to f of a, and I know that 0 is also equal to g of a. Again, this is just for the sake of the example. It's not necessarily the case here, but we're going to use it to get an idea of what's going on here. So that means that we're going to have that this is the same as the limit as x goes to a of f of x minus f of a divided by g of x minus g of a. All right, again, this doesn't look like it's helping at all. What is the point of writing all of this if I'm not going to use it? Well, if I look at the formula for the derivative, I'm kind of starting to get there, right? I have f of x minus f of a. Here I have f of x minus f of a. The only thing is that I need to divide by x minus a. Okay, so what happens if I divide by x minus a? Let me just try to do that. I'm going to divide by x minus a over here. And then we say, well, kind of a problem, because if I divide the numerator by x minus a, I also have to divide the denominator by x minus a. So let's see what happens if I divide the denominator by x minus a. Hey, look at that, we got lucky. If we divide the denominator by x minus a as well, we have that at the denominator, we also end up with the definition for the derivative. It doesn't look like it's that bad. So I have the limit when x goes to a of f of x minus f of a divided by x minus a. So that's the numerator. And at the denominator, I have g of x minus g of a divided by x minus a. And this means that if these things do exist, this is pretty much like the derivative. This is going to be similar to the derivative at a. And this is going to be like the derivative of g at a. Okay, so a lot of manipulation of things, kind of just out of nowhere. Why do we even care to make this equal to the derivative? Well, look at this. What we have now is that if I want to evaluate the limit of f over g when both the numerator and the denominator are going to 0, and what I can do is just evaluate the derivative of both of the functions when x goes to a, and it looks like it's going to give me the same as the limit. Okay. So if I just erase everything in between and write both sides of the equation, there's going to be a slight change on the right-hand side here. I get that the limit when x goes to a of f of x over g of x, which remember was of the form 0 over 0, this is going to be equal to the limit when x goes to a of f prime of x divided by g prime of x.
Is it not a, f prime of a?
Okay, so it is almost f prime of a, but look at this. We can actually generalize that because we don't necessarily know if f prime of a over g prime of a that also might be equal to 0 over 0. So we're only going to be looking at the limit of that. And if this ends up being 0 over 0, then we might just be able to take the second derivative or the third derivative, or as many as we need in order to get the result over here. So that's why I only use the more or less equal to in this case, because we can't necessarily assume that these two things are going to be different than 0.
Okay, thank you.
So I'll just do an example. I'll formulate the actual theorem next time, but I'll do an example so that you get at least just a taste of why this might be useful, and why it's important. So did everybody finish writing? Is there anybody that hasn't finished writing yet? All right, so I'm going to go to the next page. If at the end of class somebody wants me to go back to the previous slide, you can ask me to. So in this example, I'm going to ask you to find, I'm going to find the limit when x goes to 0 of e to the x minus 1 divided by 2x. Now, these limits were easy to evaluate. These limits were super easy to evaluate. You just have to factor and cancel some terms. This limit over here, though, is not as easy to evaluate. We have to, we can start by plugging in. And if we start by plugging in, we're going to have that this is e to the power of 0 minus 1 divided by 2 times 0, which is equal to 1 minus 1 over 0, which is equal to 0 over 0. And this doesn't work. Okay. And then I can try to factor something at the numerator and at the denominator, but there is not really a term that I'm going to be able to factor at the numerator and denominator that will allow me to simplify this, right? I can't really factor anything from the numerator that I'll be then able to simplify with what I have at the denominator. So that means the factoring technique in this case doesn't work, which is why you wouldn't have had this type of example in Calculus 1 last semester, because you didn't have any techniques in order to solve this. Instead, what we're going to do is use L'Hopital's rule. So here I'm going to write equal, and then based on L'Hopital's rule, this should be equal to the limit as x goes to 0. And I'm going to find the derivative of the numerator and the derivative of the denominator. So the derivative of the numerator is going to be e to the power of x, and the derivative of the denominator is going to be 2. Once you have found the derivative, you can try to plug in again. If you get a result, then you get a result. If not, then you might have to take the derivative again. So derivative of this evaluated at 0, e to the 0 is just equal to 1. And then you have divided by 2, so this is 1/2, and you're done. You got a result. Now, this was all from this point over here, which means that the limit as x goes to 0 of e to the x minus 1 divided by 2, which was equal to this over here, is equal to 1/2. And we're done with the problem. Really easy to evaluate once I have L'Hopital's. Do I have any questions? All right. Oh yeah, Colin.
Yeah, so I'm not sure where does the 1/2 come from?
Oh, if I plug in 0 into the e to the x, it becomes e to the 0.
Okay, yeah,
Yeah?
now I understand, yeah.
Okay, so this is just e to the 0. Maybe the step that I missed over here is to write e to the 0 over 2.
Okay.
All right. So this is, the denominator is missing an x. No, Juliette, it's not missing an x. It was 2x over here. What I'm doing here is find the derivative of the numerator and the derivative of the denominator. Right, so I'm using this theorem over here, which I haven't formulated yet. I'm just using it now for the first time. I'll formulate it next time. So what I said is the derivative, the limit of one function over another function, if the result is 0 over 0, which it was in our case, it's going to be the same as if I take the limit of the derivative of the numerator divided by the derivative of the denominator. So in this case, derivative of the numerator is just e to the x, derivative of the denominator is just 2, and so that means that the limit of this thing is going to be equal to the limit of the derivative of each, the numerator and the denominator. That make sense yet? Oh, originally it was e to the x minus 1. But then I found the derivative of the numerator, which is e to the x. I found the derivative of the denominator, which is just 2. And then I plugged it into the new function that I have, which is the derivative of the numerator and the derivative of the denominator. So I started with this, this limit that I wanted to evaluate. I differentiated the numerator, I differentiated the denominator, and then I plugged into the new limit that I evaluated. At the end over here, I'm just writing, because I started with this limit over here, and through equations, I found this answer, then that means that the limit of this function over here is going to be equal to the result that I found, which is 1/2. Is that good? Yeah.
There's something I don't know. Can I use the annotation?
Yeah, absolutely.
How do I do that?
Let me see if you have it enabled. Okay, you have it enabled. You can go to more options or options or something like that.
Okay.
And annotate.
I'm wondering why, since this is still like this, why does this not stay this?
Oh, absolutely. Yes. Okay. Thank you.
Okay.
Yeah, that should be an X. Absolutely.
Perfect. Okay, thank you.
Yeah. That's good. Thank you. Yes, that's an X. Very good. It's just me being distracted. Okay, so you have e to the x minus 1 over 2x, otherwise it would have just been 0. So that's good. Yeah. All right. Any questions?
Yeah, I do.
All right, what's up?
If you evaluate that's the 2x that you just added there, doesn't that become 1 over 0?
Now it becomes 0 over 0, which is what we had at the beginning.
Oh, right. Okay, thanks.
Yep. Okay, so this is the first example that we're going to do. Don't worry too much about this. We're going to do a bunch of other examples next time. I just wanted to get started with the material so that you have a bit of an intuition of how to use this, but try to focus on the practice set, on the web work for differential equations. I'll also be announcing on Thursday the evaluation plan for the rest of the semester. So there are some things that are going to change with respect to, of course, the number of tests, the type of tests that we're going to have. It is not clear what we're doing with final exams just yet. And so on Thursday, I'll give you an update about what the math department is doing and how we're going to be running tests in our class. Is that okay for everyone? Yeah. Do I have